More partial fraction decomposition integration fun. This time we've got a fraction here. The first thing we want to do to check here is the degrees, right? The question is, are we going to have to divide first? The degree on the top is 3. The degree on the bottom is not 2 because we're squaring x squared, so it'll be x to the 4th. So the degree on the top is smaller, so we do not need to start with any division. We're going to jump straight into the partial fraction decomposition. And this time it's already in factored form. That saves us a step. And we've got a repeated irreducible quadratic as our denominator. So when we've got that repeated factor, we're going to do the same thing we did last time, where we're going to start with one factor in the first denominator, and we're going to move on to a double factor in the second denominator. And the other thing is, remember that if it's a quadratic, then we don't want to put a constant up top. We want to put a linear expression. So we need an ax plus b, and this is going to be a cx plus d. So when we defractionize this, multiply by the common denominator of x squared plus 2 quantity squared, we get ax, or 8x cubed plus 13x equals x squared plus 2 cancels out with one of the x squared plus 2's, but the other x squared plus 2 gets multiplied by the ax plus b. And over here, both of the factors get canceled out, so we get cx plus d. All right, so rewriting the right side of the equation, when we distribute, we get ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. And then when we group these together, we've got a x cubed, and that's actually the only x cubed we have. We've got a b x squared, and that's actually the only x squared we have. We've got a 2a and a c times x, and we've got a 2b and a d times no x's, right? 0 x's. So that gives us our coefficient of 8 for x cubed. Our coefficient for x squared is 0. We have 0x squared. That makes things easier. We've got 13 for our linear coefficient, and we've got 0 for our constant. So while we do have 4 unknowns, a, b, c, and d, the system is actually pretty easy because we've got a equals 8 and b equals 0, which means that c equals, well, if a equals 8, we've got 16 plus c equals 13, so c has to equal -3. And if b equals 0, then we've got 0 plus d equals 0, so d equals 0. So zeros make things easier, so we find out that this works out to be, or not to be, no, it is to be 8x over x squared plus 2 plus -3x over x squared plus 2 squared. All right, for the sake of space, I'm going to go ahead and delete all of, well, maybe I'll just move it off to the side so that we have room. That didn't work. We'll try again. Goodbye. What is one not doing? Goodbye. All right, so now we can integrate this. We're going to integrate this original integral is equal to a new integral of 8x over x squared plus 2. I'll go ahead and change that to a minus 3x over x squared plus 2 quantity squared. And we'll notice that both of these denominators have an x squared plus 2. Both of the numerators are a linear So the U-substitution process might be an attractive one here. We'll let u equal x squared plus 2, so du over 2x equals dx. Let's save a little time here. So when we do some substitution, we'll replace the x squared plus 2 with a u. We'll replace the x squared plus 2 squared with a u squared. And we'll replace the dx with a du over 2x. Joy of joys, the x cancels out in both of these places, which is nice. Sometimes we have to deal with two separate integrals, but this one we can do in one fell swoop. So we've got 1/2. I guess I'll factor out that 1/2. And then we've got 8u to the negative 1 minus 3u to the negative 2. And these are each baby integrals that we can deal with no problem. The negative 1 for the exponent means natural log. And the negative 2 for the exponent means inverse power rule. So the negative 2 adds 1 to it to get negative 1, and then we divide by our new exponent, negative 1. And we've integrated, and now we can sub back. We've got 8 natural log the absolute value of u, which is x squared plus 2, minus a negative, so plus 3 over x squared plus 2. And if you feel like distributing the 1/2, that's perfectly fine. Then you'd get 4 here, and you'd have a factor of 2 in the denominator. Whatever. Just one more example of partial fraction decomposition. Which brings us to our last example of integration using partial fraction decomposition. This time, you knew it was coming. All the other examples were proper fractions. This one is improper. And we know that because the degree on the top is larger than the degree on the bottom. So our first step is to make it proper by division. And we can't do synthetic division because it's a quadratic denominator. So we'll go ahead and do the long division. And when you do the long division, you get 2x. I'm going to go ahead and skip all this because you guys don't need to watch a review of polynomial long division. Our remainder works out to be negative 2x plus 5 over x squared plus x minus 2. Okay? So if you need some help with polynomial long division, you'll have to look at another place because our videos get long enough as is. So this factors to x plus 2 times x minus 1. And now we've got something we can integrate and something we can integrate and something that we need partial fraction decomposition for. So we'll take negative 2x plus 5 over x plus 2 times x minus 1. That's going to equal a over x plus 2 plus b over x minus 1. So negative 2x plus 5 equals a times x minus 1 plus b times x plus 2. So we have an ax and a bx, so that's a plus b times x. We've got a negative a and a 2b, so minus a plus 2b is our constant. So a plus b equals our coefficient of negative 2. Negative a plus 2b is equal to our constant of 5. That's set up nicely for elimination, right? When we add these, the negative a and the positive a are gone. So 1b plus 2b is 3b. Negative 2 plus 5 is 3, so b equals 1. If b equals 1, then a equals negative 3. So now we've got a negative 3 over x plus 2. And we've got a positive 1 over x minus 1. And each one of these fractions is very simple to integrate. So now we can rewrite our integral one more time by taking that one big fraction and breaking it into partial fractions of negative 3 over x plus 2 and a positive 1 over x minus 1. And then we can just integrate, which is great. 2x integrates to x squared. Negative 1 integrates to negative x. We've got the natural log going on this next one. We've got the natural log going on this next one. And since the derivative of each of these denominators is simply 1, we don't have to worry about any U-substitution or anything. So we've got our final answer. Unless you feel like condensing those logs, which I'm not going to bother, but you can if you like.